Okay, hello everyone. In this video we have section 6.2, which is on line integrals. So this section is going to seem very similar to what we did in section 13.3, finding arc length, and it's a big part of it. And it's at first it's not going to seem to be related to vector fields at all, what we did in the last section, but then we'll make a connection to that at the end. Okay. So let's talk about what a line integral is. Okay, first think about what we did in chapter 15 when we integrated multivariable functions. Okay, so what would we do? We would integrate on a region D. And what would that region be? Let's see, I must have erased it at some point accidentally. Remember, we would be integrating on like a region R2, right? So maybe we'd be integrating on like this region in the XY plane. Okay. And then on that region, you know, our function is that surface. And so if we integrated that our function, our multivariable function on this domain, this two-dimensional domain, what would we get? We would get the volume beneath the surface, or the volume under the surface. Okay. So that's what our multivariable integral gives us, right? But what if we don't what if we kind of restrict our domain? So instead of integrating on this blue square, okay, this blue square in R2, what if we only integrate on a strip? Okay, so what if we still have our multivariable function giving us this surface, but then instead of integrating on this domain, what if we just integrate on this strip here, this line or this curve, whatever you want to call it? What if we just integrate on this curve? Okay, what would that give us? Okay. So we would just integrate on this curve. So let's say we have, you know, this whole surface above that square, and we're just considering integrating on the blue curve. Okay. Well, just forget about the rest of the curve and just kind of think about the surface, you know, above that that line. Okay, just think about the surface that corresponds to that strip in the domain, right? So we'd have something like that basically, right? Kind of a curtain. Okay, so let's say it's this. Okay, so if I integrate on just that strip, what am I looking at? What kind of quantity am I going to get out? Well, we can see right away that the integral of this thing's not going to give us a volume, right? You know, when we were talking about integrating on the whole domain, we would end up with a volume. But now if I'm just integrating on that curve, well, there's no way that can be a volume, right? It's not, doesn't have any substance to it, right? That you know, that curtain doesn't have any volume to it. Maybe it has some area though. And that kind of makes intuitive sense, right? Maybe we could, instead of talking about the volume, maybe if we integrate along, this strip in the domain, okay, maybe that will give us the area of that curtain, so to speak. You know, if I think of this kind of surface here, maybe if I think of that as a curtain, maybe integrating along that curve in the domain will give me the area of that kind of curtain. All right, so that is what that quantity is going to represent. And once again, we developed this theory up from the Riemann sum. Okay, so we're integrating, we start by approximating. We want to kind of approximate this area with rectangles, right? Now, so I want to break this up into rectangles, right? And the rectangles have a base and they have a height. So let's talk about the base of these rectangles first. Well, it depends on the curve. You know, let's call this curve C. That's the curve inside the domain we're integrating along. It really depends on our curve C. But for now, and we'll talk about how we get it. But for now, let's call this base of each rectangle this delta S, right? And what about the height of these rectangles? Well, that's coming from my function values, right? This strip up here is my function fx y. Okay, so basically I take a point in this domain and I plug it into my function and it gives me a height up here. So it's going to be the height of these rectangles are going to still be my functional values along that curve. Okay. So what would my Riemann sum look like? Well, it'd be a sum like this, where I'd be adding up the base of my rectangles multiplied by the height of my rectangles. Okay, and then I take the limit as I make those rectangles narrower and narrower. And what do I get? Okay, as with usual, I get my summation sign becomes an integral sign. My functional values at these select points become just my general functional values, fxy, and then my delta s becomes my ds. Okay, and maybe these are pretty evident, right? I'm integrating along that curve and I'm integrating my function, but then the question is, okay, well, what is this ds? Okay. In order to evaluate these integrals, we'd like to be able to rewrite this ds in terms of x and y, right? And this is kind of where our material from 13.3 comes in. We know from 13.3, think about that ds as the length of that rectangle along this curve. So it's kind of like the length of the curve along, this section. Okay, so it should be related to arc length somehow, right? So we know from section 13.3 that if we write this curve, let's say we write this curve in 2D. Let's say we write this as r of t equals x of t, y of t. We have this parametric curve. Okay. If we write it like that, then ds, we know our arc length is going to be what? The integral of dx dt squared plus dy dt squared dt. Okay, remember that's my arc length. Okay, which we represent as s. And then think about like differentiating both sides. We would have ds is equal to the square root, what I've written here. ds would equal square root of dx dt squared plus dy dt squared dt. Okay. So what does this mean for our integration along these curves? Okay, so if I want to integrate my function along a curve C, where C has a parametric description like this, C is equal to x of t, y of t. I've written it as this parametric function here. Then my integral is going to, which I've kind of written symbolically here, I'm going to be able to rewrite as, well, the ds is going to be replaced with this, right? And then what's happening with our fxy, right? If I'm integrating, I've changed this to an integral in terms of t, right? So I want these x's and these y's to be in terms of t. Okay, so I take my parametric description for x and y on the curve, and I just plug it in for my x and y values. And then my a and b are going to be like my starting point and my ending point of my parametric curve. Okay. All right. So if you've followed that so far, great. If not, let's look at this example real quick and see exactly how it works. So what am I doing? I'm integrating x times e to the power y along C. Okay, that's what this notation means. if you see the integral sign with C here, that means like I'm integrating along a curve, and then we describe the curve, and we're told C is the line segment from 2, 0 to 5, 4. Okay. And then ds here is meaning I'm integrating along that curve. Okay. So let's consider this curve C first. Okay, so this is my curve. It's pretty simple. It's just that line segment from 2, 0 to 5, 4. So think about it like this. I could think of this as like a three-dimensional thing. You know, I could think of this as three-dimensional space, and I'd have my, you know, curve, and then I have its heights, and then I kind of draw the curtain. But let's forget about the three-dimensional stuff for a second and just look at the domain. All right, so this is what I'm integrating along. Okay. So let's figure out a way to describe this curve as a parametric function. So I want to be able to write this curve. I want to be able to write it as r of t equals x of t, y of t, where this is the important information here, x of t, y of t. So how can I write this line segment in this form? Okay. So this is kind of going back to what's chapter 12, this writing the equation of a line in like vector format. So what I'm going to do is I'm going to take the initial point, 2, 0. Okay. And then I have t plus the vector between the two curves. Let's see. So the vector that connects 2, 0 to 5, 4, well, that would be 3, 4, right? For t between 0 and 1. Okay, so that's my parametric description of my curve, my line segment. Okay. So what does that tell me? First, I'm integrating along this curve, and I figured out this is my parametric description of the curve. So my integral, and let's see, my t equals 0, that would be my starting point, right? If I plugged t equals 0 into my parametric function here, I would just end up with the 2.20, which is my starting point. Okay. And then if I plugged in 1, I would end up with the 0.54, which is my endpoint. So I want to integrate this from 0 to 1 in terms of t. Okay. Now I want to integrate what fxy and then dx dy, dx dt squared, dx dy squared. Okay. Now it might be a little confusing because this doesn't really match this, right? But we can combine this into a single vector to get it to kind of match a bit better our idea of what should be going on. I could rewrite this as 2 plus 3t and 4t, right? Okay, and now I have this nice format, x of t, y of t in there, right? Okay, so what's my x of t? 2 plus 3t. What's my dx dt? 3. And then I want to square it. What's my dy dt? 4, and I square it. So what is this term? Remember, this is my dx dt squared term plus dy dt. Now I'm integrating this thing in terms of t, so I want this x and this y in terms of t. Okay, so from my parametric description, I know x is equal to 2 plus 3t, and y is equal to 4t. Okay. So instead of having fxy, I want f of 2 plus 3t, 4t. Okay, and then what is our f? Okay, what function are we trying to integrate? Trying to integrate x e to the power y. So I'm going to rewrite this with that function, and I'm just replacing x with 2 plus 3t, y with 4t. Okay, this is what? Square root of 25, which is 5. And so my integral becomes this. And let's see, this is fairly easy. We might need a little integration by parts. I'm trying to do this in my head, so this should be right. Okay, now evaluating, let's see. We have this. And then you guys can simplify on your own. That should be our answer. And let's see, is this a problem from the book? Yeah, but it's a weird number. So we'll have to see if that's, you'll just have to see if that's right or not. Okay. I'm going to lay out some steps in just a moment that will maybe make it, easy for you to do methodically if you're having trouble kind of seeing the intuition behind this. But first, let's kind of introduce a new complication. Okay, so these problems become more complicated the more complicated our curve C becomes. All right, so in particular, C might be what we call a piecewise smooth curve, meaning it's made up of a bunch of pieces of functions. Okay, so for example, this green curve here. Well, let's say this is the curve y equals x squared when x is between -1 and 1. And then from here, what do we have? We have y equals x from x equals 1 to x equals 2. And then we have y equals 2 from x equals 2 to x equals 4. Okay, so we have this kind of piecewise definition of our function, of our curve. Okay, so that makes things maybe a slightly more difficult, but it's really just one extra step. So here are the steps to solve these problems, and then we'll do some examples and maybe you'll be able to follow along. Okay, so these problems are all about, let's reiterate what we're doing. We're integrating a function along a curve, and this is the notation you're going to see. Okay, you're going to see an integral sign with C, and then they're going to tell you what C is. C equals blah, blah, blah. They're going to describe the curve. You have a function inside the integral, and then you have this ds. Okay. And this ds means we're integrating along the arc length. And that might not mean anything to you right now, but we're going to discuss that more in a bit. This is kind of the standard version of the problem. Okay, so how do we deal with this problem? Okay, this curve C, at its most complicated, it's going to look like something like this, where it's a bunch of different functions kind of pasted together. Okay, so step one, break that curve up into the recognizable pieces or functions, and then we want to make an integral for each piece. So for this type of complicated curve, I would need to figure out the function for each of these pieces. Okay, and I'm gonna do this process for each piece essentially. Okay, step two, you need to parameterize each piece of the curve. Okay, so what does that mean? Now we've done this in this course already. I want to write, let's see, y equals x squared, that first piece of this green curve, right, for x between -1 and 1. I want to write this as a vector valued function. I want to write this like this, where both of these depend on a parameter t. Okay. So how can I do that? Well, you're going to have to go back and review that section. I assume it's in chapter 13 somewhere. You're going to have to go back and review on how to do that and get a little practice. For this curve, it's fairly easy. We just let x of t equal t. Okay, and if x of t, if x equals t, if that's our parameterization for x, to find y, what's y of t? I just plug this in for x here, and I see, okay, y of t is equal to t squared. So my parameterization for that first function, for that first curve, is t squared. Okay. For what are my t values? What are my starting points and ending points here, right? So I want to find the t. I want to find the value of t that I plug in to my parameterization to get my starting point. Let's say this is my starting point. And then what's the value of t that gives me that ending point? Well, these are my starting points and ending points for that particular curve. Okay, and then I repeat the process. I find the parameterizations for, now I need to find the parameterizations for this piece of the curve and this piece of the curve. And these are fairly straightforward, they're lines, right? So the parameterizations are fairly easy. And let's see, they kind of give a little comment. So comment number, or let's see, box number 8 in the textbook is kind of on page 1119 of the textbook, which, let's see, I don't think they give page numbers in the ebook, but let's see, after example 3 in the textbook, we have, let's see, lines 5, 6, 7, and then line 8, which is displayed as like a blue 8 with a box around it, and then it gives this formula. Okay, and that kind of discusses making parameterizations for line segments. All right, so that's step 2, right? So step 1, we break up the curve into recognizable pieces or functions. Step 2, we make one of these parameterizations for each piece of the curve. Step 3, we need to integrate along each piece of the curve. We need to make an integral for each piece of the curve. So we convert each integral from integral in terms of x and y, ds, and we convert that into everything in terms of t, whatever our parameter t is. Okay, so remember how that works. We find our parameterization of our curve, right? Which should look like one of these vector valued functions like this. Now we plug this x of, whatever this x of t is, we plug it in for our x's in our function. And where this y of t is, we plug that in for our y's in our function. Okay, so our function becomes this. And then we have this this term, which is, this is giving us our ds, right? We have square root of dx dt squared plus dy dt squared dt. And then we're integrating in terms of t. Okay, so in step 3, we're setting up the integral. Step 4 is just integrating all those pieces and then adding them together. Okay. So let's see a quick example. Okay, and this is one of these piecewise smooth curves. So this is example 2 from the textbook. So let's see, I haven't tried it yet. Let's see if I can do it here, and let's see if we get the same answer that the textbook does in example 2. I want to integrate this function, 2x. I have my integral sign here, where I have integral along C, our curve C, and then I have 2x ds. So I'm integrating with respect to arc length. Again, we'll talk about that in a minute, what that ds means as opposed to something else. We're integrating along this curve, and then we're told C is the curve y equals x squared from 0, 0 to 1, 1, and then the vertical line segment from 1, 1 to 1, 2. Okay, so let's draw our domain real quick. Or not even our domain, our curve, right? Let's draw our curve. Let's see, y equals x squared from 0, 0 to 1, 1. Well, that would look roughly like this, right? We have 0, 0 here, 1, 1 here. And then our curve from there, our curve is the vertical line segment from 1, 1 to 1, 2. Okay, so this is what our curve C looks like. This is our curve C. Right. So this obviously has a couple pieces, right? This parabola piece. First we have y equals x squared, and then we have that vertical line piece. All right, so let's go through this step by step. Let's see, what's step 1? We break the curve C up into recognizable pieces. Okay, so 1. Well, we have y equals x squared for x between 0 and 1. And then we have what? It's really the curve y, or no, excuse me, x equals 1. That's how we write that vertical line segment for, let's see, y between 1 and 2, right? All right, so those are our pieces. And, you know, writing this stuff down is not super important, but we got to be able to, you know, the next step is more important, writing parameterizations for each of these, right? Okay, so step 2, we need to write parameterizations. We need to parameterize each of those curves. Okay, so what's the parameterization for this? Y equals x squared. I need to write this as like a function r of t equals x of t, y of t. Well, once again, I could just let x equal t, and then y equals t squared, right? So my parameterization for this piece of the curve would be t squared. Okay. And then what are my values of t? Now, this time t is between 0 and 1, right? If t equals 0, I'd be there. If t equals 1, I'd be there. Okay. Now I need to parameterize this piece of my curve. Okay. Okay, so this is my first curve. And really, this is what I'll need all this information. Okay. That's my first curve. And then I need to make a parameterization for that vertical line. Well, how could we do that? I'm going to take my starting point, which is 1, 1, plus t times the vector between these 2 points. What is the vector between these 2 points? This vector is, it moves 0 units in the x direction, 1 unit in the y direction. It's this. For t between, again, 0 and 1, right? So this I could write as what? 1 plus t. Okay. All right. What's our step 3? Convert each integral. Okay, so now I'm keeping my integrals separate. Like I need an integral for each of these pieces of my curve. Okay, so let's talk about the first integral, the integral of the first piece. So we got f of x, y, ds, right? And I want to talk about the integral along my parabola. Okay, let's go back up to that parameterization. First of all, my integral sign, what are my bounds for my integral? Well, it's my t bounds, right? Let's see. Yeah, it's my t bounds, okay? So what are my t bounds for this piece? 0 to 1. Okay. And then I have my function. Well, what is my function? 2x, right? But I want to replace this x with x of t. What is x of t on that piece? X of t is just x of t equals t, and then y of t equals t squared. So 2x becomes just 2t. Okay, and then ds, well, that gets replaced with that, what, dx dt squared plus dy dt squared. Okay, dt. Well, what's dx dt? That's coming from this, right? So what's dx dt? What's the derivative there? That's just 1. What is dy dt? 2t. T squared, all right? So that becomes 4t squared. Okay. And this is my integral, and then I have my dt. So this is my integral for the first piece. Okay. So I need this. And now what's my integral for the second piece? My second piece of the line segment. Okay, so I need an integral for that. Okay. This is my information for the second piece. Well, what are my t-bounds? Once again, my t-bounds are 0 to 1. It's not a problem that the bounds are the same for these two different pieces. That's not a problem. What's my function? 2x. And again, I'm replacing x with my x of t. Well, what's my x of t in this case? It's just the number 1. Okay. Now I need my dx dt squared plus dy dt. Well, what's my dx dt in this case? Okay, well, x of t is 1, so dx dt is 0. What is my y of t? 1 plus t. So what's my dy dt? 1 squared. Okay, so this is just the number 1, right? So I just have the integral 0 to 1 of the number 2 dt. Okay. So these two integrals are what's going to give me my line integral. Okay. So now step 4, I integrate these things and then add those numbers together. Okay. So first I integrate 0 to 1. What, 2t square root 1 plus 4t squared dt. And then I need to add the integral 0 to 1 to dt. Okay. This integral should be a u sub, right? We could do u is equal to this stuff inside. So u is equal to 1 plus 4t squared. Du is equal to what? 8t dt. Okay, those cancel, only get 1/4. So when I evaluate that integral, I should get what? I plug in 1, I get 5 to the 3/2. I plug in 0 and I get 1. So 1/6 times 5 to the 3/2 minus 1. And then, let's see. So that's this integral here. What's this integral? Well, this integral is really easy, right? It's just 2. All right, let's see. Integrate 2t, 1 to 0, 2. Okay. Then I add these pieces together, and that should give me my answer. And let's see if that matches the textbook. Yeah, it does. They've written it slightly differently. They've written it as 5 square root of 5 minus 1/6 plus 2. Well, these 2's are the same, and then these are the same as well, which you can see if you work that out on your own. Okay, so that's our answer for that problem. Okay, and it's all just about following these steps. And remember what this is giving us. You know, we have a curve. You know, we're integrating this curve along this we're integrating this function along this curve. You know, in 3D, what would this look like? This curve would look something like this, right? And then we have this function up here, you know, that's giving us this whole surface, and we're integrating that function along this curve, and it ends up giving us, you know, kind of the area of the curtain that connects this function to that curve. So it's giving us this area of that kind of curtain looking thing, you know, and I don't know what this function looks like. I was just drawing something. Okay. Everything works the exact same in 3 dimensions. Okay. Just maybe a bit harder to picture, and maybe it's not quite as clear, you know, what the geometric intuition is. So remember, when I say, okay, this integral gives us the area of that curtain, that's just a nice little intuition to have. That's not the definition of that integral. That's not, you know, the end goal always. You know, this integral is just a general tool to use. Okay, so when I say area of that curtain, you know, that's just like a little geometric intuition to keep in the back of your mind. Okay. Now, in what were we doing? We were integrating. We had a function fr2 to r. Okay, and we were integrating this. You know, that should give us a surface, like a surface. We were integrating that along a curve in R2. Okay, so think about this. Okay, we're integrating along this curve. You know, what we just did was we integrated along a curve in R2. And what does the graph of that function look like along that that curve? You know, so if I just considered the function, the output of that curve, you know, the graph would look like this. I have the curve in the domain, and then maybe this is the functional values, and I kind of combine those and I get this nice graph. Okay, so that's what everything looks like in this case where we have a function of 2 variables. But we can do the same process when our domain is in 3 variables. Okay, so let's say now we have a function R3 to R. Okay, so now, and then I want to integrate it along a curve C in R3. So now my domain is 3-dimensional. So I have this 3-dimensional domain, and I'm integrating along this curve in R3. Now, what does the graph look like? Well, we don't really have we can't really picture the graph of a function from R3 to R, right? This would need to be like, we would need to be able to draw in 4-dimensional space. You know, we can't really picture that. We can't really draw that very well. Okay, so this, maybe there's not as much geometric intuition. You could kind of think of it as the same kind of thing, like sort of the area of a curtain, but like a 4-dimensional curtain, you know. So, you know, the geometric intuition stuff can be helpful, but don't hold on to it too tightly. Otherwise, you're just going to like confuse yourself when you have to start thinking in higher dimensions. So, you know, just keep a loose idea of what we're doing, but don't try and tie it to any kind of real geometric thing too tightly. Okay. The short story is all the previous steps we laid out work in this higher dimensional case as well. We just add terms for the z component. Okay. So what are we doing? We have a function of 3 variables, and again, we're trying to integrate it along some curve in curve C. But now this curve C is in 3-dimensional space. Okay. Well, we do the exact same steps. The only difference is, okay, my curve C, you know, in the previous case, in the 2-dimensional case, we wrote it as x of t, this kind of vector valued function like this, x of t, y of t. Well, now in 3 dimensions, we're going to write it as x of t, y of t, z of t. In my 3-dimensional function, I'm going to replace x with x of t, y with y of t, and then z with z of t. Okay, so just like we did in the previous case, we're just accounting for that z term. And then for this ds, what is ds? What is ds going to be? ds is going to be square root of dx dt squared plus dy dt squared plus dz dt squared dt. So nothing too complicated. It's really very simple to account for that 3rd dimension. Let's see if real quick I can find a 3-dimensional version or 3-dimensional problem for you guys. Not one that I want to show you yet. Oh wait, no, here's one, number 12 in the textbook. Okay, so it's another even problem 1. So will I be correct? Will I be wrong? I'll let you decide. Number 12, we want to integrate x squared plus y squared plus z squared. Okay, we're given this problem. And then we're told C is equal to the curve. And then they actually give us the parameterization for the curve. They say C is given by this, x equals t. Y equals cosine of 2t. Z equals sine of 2t. For t between 0 and 2 pi. Okay, so what's going on here? They've kind of done the first 2 steps for us, right? So first, step 1 is break our curve C up into pieces as necessary. Well, this is just one. C is just made up of one curve, right? Okay, so that's done. Or that's, you know, doesn't need to be done. Step 2, find the parameterization for the curve. Well, this is what they've given us. They've already given us that. They're saying C is equal to that vector valued function t cosine of 2t sine of 2t for t between 0 and 2. Okay. All right, step 3. Convert those integrals or make those integrals. Okay. So I'm integrating C. Okay, what are my bounds for my t? Okay, 0 to 2 pi, right? So I know my bounds of integration are 0 to 2 pi. My function, I want to convert that to my, I want to replace my x, y, and z with the x of t, y of t, z of t I have for my parameterization. Okay, so let's see, x squared becomes t squared. Y squared becomes cosine of 2t squared. Z squared becomes sine of 2t squared. Okay, and then I'm running out of space here. What does my ds become? ds becomes dx dt squared, dy dt squared, dz dt squared. Well, what's dx dt? dx dt is 1, and then I square it. Okay. What is dy dt? dy dt is negative, let's see, negative 2 sine of 2t, right? And then I square it. Okay, what's dz dt squared? Okay, well, dz dt is 2 cosine 2t. I square it, then I have a dt. Okay, so let's simplify everything. That integral should become 0 to 2 pi t squared. Okay, t squared, and then we got cosine squared plus sine squared. And it doesn't matter what's inside, you know, it's the same, right? 2t, 2t. So that term should be 1. Okay, cosine squared plus sine squared is equal to 1. Then I have square root. Okay, I got 1 plus 4 sine squared 2t plus 4 cosine squared 2t dt. Okay, simplifying further, let's see. Again, I have sine squared plus cosine squared. I got 4s now, so I'm going to count for those 4s. But it simplifies to just square root of 5. So I just have integral 0 to 2 pi. I bring out the square root of 5, t squared plus 1 dt. That's an easy integral. Two pi to 0. And that becomes what? 8 pi cubed over 3 plus 2 pi. Yeah, we're done. That should be the answer. Let me know if you get something different. The steps are identical. You know, we didn't have as many steps because they gave us a lot of information from the start, but the steps are identical. We just got to count for that extra dimension. So now I'm going to do an annoying, variation of what we've been working on. The idea of the line integral that we've covered so far is pretty straightforward, I think, especially when we have a curve in 2D. You know, the line integral intuitively gives us the area of that curtain. Okay. Now that is when we integrate along the curve. So I said we would talk about this kind of notation. We're looking at integrals of the form fxy ds, meaning we're integrating with respect to arc length, meaning we're integrating along the length of that curve. Okay. All right, so that kind of makes sense with when we're talking about the area of the function of that curtain, right? We look at the height of these rectangles that go along the curve, right? That's essentially what we're doing. Now, there's an annoying variation in the textbook that we need to learn. it doesn't make much sense until the end of this section. Okay, so it's gonna be a little weird at first, but then it has a useful application in just a few moments. Okay, so instead of integrating along the curve, okay, so if we're looking at this, instead of integrating along this curve, what if we have the same curve, same setup? We still have that same kind of curtain, but instead of integrating along the curve, we integrate along the x-axis or the y-axis. Okay, now what's going on? What's the kind of what's the intuition here? Okay, and this is something even, I don't have a super good grasp on, so I kind of looked, and you might notice if you look at the textbook doesn't give any kind of intuition about what is going on here. So what are these line integrals with respect to x or with respect to y? Now let's see if it should be, I should have it pulled up here. So I did some investigating to try and find, some geometric intuition for you guys. And I found something on Mathematics Stack Exchange. Now for, those of you who are going to go higher in math, you can see the URL up at the top of the screen, math.stackexchange.com. This is the website you go to for advanced math help. If you guys are, I hope you're not using Chegg or whatnot on the tests, but if you ever need help, maybe you go on, some website and you ask a question. Mathstackexchange.com is where you come to ask kind of advanced questions. And this is not too advanced. It's like calculus stuff, but you could ask. There are mathematics professors and professional mathematicians who come on here and talk. So there's a lot of advanced knowledge on this site. All right, so what you're looking at here in this first image is the line integral along our curve with respect to arc length, right? We have that curtain. We're talking about that area underneath of the area of that curtain. Okay, now that's when we're integrating with respect to ds. Okay, with respect to arc length. Now, if we integrate, and now maybe you can kind of see what's going on here, okay, with those these red and blue lines. Oh, excellent. Now, instead of integrating along the curve, we want to consider integrating along that bold red line, just along the x-axis, or maybe along that bold blue line along the y-axis. Now, what kind of quantity would that give us? Would that give us the area beneath the curve? No. So like maybe if we integrated along the x-axis, we'd get, this kind of area. Okay, so not necessarily the area of the curtain, but maybe like the area of the shadow of the curtain along the x-axis. And then maybe we'd get something similar if we integrated along y, but in this example, that wouldn't necessarily be the case because this curve kind of loops in on itself. Okay, so maybe you could think of these integrals in that in those terms. Okay. But the book doesn't give any of this kind of intuition, so and it's I kind of will follow their lead and say it's that kind of intuition is not too important. Let's talk about how to compute these values. Okay. Okay. So now, and this is how the book will indicate that you're supposed to do integrate along x. So what were we seeing in the previous sense? In the previous cases, what we were looking at was we were integrating along a curve, and the notation we used was this. We were integrating along a curve C with respect to arc length. Okay. Now what we're doing is we're integrating along that curve C still, but now we're integrating with respect to x. Okay. Now, the only difference is we still kind of follow a lot of the same steps, which you'll see here. We still break the curve up if necessary. We still find the parameterization the exact same way. We parameterize the curve C. And then the only difference is in step 3, how to convert each integral. Okay. Now, instead of having that square root dx dt squared plus dy dt squared term dt, instead of having this, we just have x prime of t dt. Okay. So it's not even squared, it's just x prime of t dt. Okay, so we drop the square root, we drop the dy dt, and we drop the square. Okay, and we just have x prime of t dt. That's when we're integrating with respect to x. If we integrate with respect to y, it's y prime t dt. Okay, and that's the only difference. Now we will usually, you'll usually see these x and y integrals together. Okay, so you'll integrate one function with respect to x and another with respect to y. Okay, and the notation for that is, let's say I'm given a problem and they tell you to integrate along this curve C. You're integrating along this curve C, and the C will be the same in both integrals. But you're integrating this function with respect to x, and you're integrating this function with respect to y. Well, they have a little shorthand that they've come up with, and it's, when I say they, I don't mean the authors of this book, it's standard notation. Instead of writing this, where they write the integral sign both times, and it's a bit long, what they do is they just write it in this kind of more compact notation. So they drop that. There should be a second integral sign, right? But they drop that and they just write it like this. Okay, so that means they're integrating along the curve with respect to C, or excuse me, with respect to X, and then they're integrating this along the curve with respect to Y. Okay, so let's see an example real quick. But before that, I'm gonna take a quick break. All right, let's see, still sharing the screen, good. Where were we? Oh, you guys don't want to see that word puzzle. All right, so we were talking about integrating with respect to x and with respect to y instead of respect to y. We saw that it's a pretty easy adjustment. Instead of having that square root, if we're integrating with respect to x, I just have x prime of t dt, and if I'm integrating with respect to y, I just have y prime of t dt. That's the only thing that's different. The how I find the bounds and how I convert the function are still the same. Okay, so let's look at this this problem. Okay, so I'm integrating e to the x dx, and it looks like it would just be a normal integral, right? Everything inside the integral looks the same, e to the x dx, but I am integrating along a curve C, where, let's see, C is the curve in R2 given by this, x equals y cubed from -1, 1, -1, -1 to 1, 1. Okay. Let's see. Okay, so just to picture that curve a little better. What does it look like? Let's see, x equals y cubed. So let's see if this is x and this is y. X equals y cubed would look like what would it look like? This essentially. No, it would look like this, right? We have -1, 1, 1, 1. All right. So I want to integrate along that curve. So first, the steps are the same, right? Step 1, for all my stuff, break it into pieces. Well, this is just one nice curve, so I don't need to break it into pieces. Step 2, all right, parameterize each piece. Okay, so now how do I parameterize x equals y cubed? Well, I could just do the parameterization y of t equals t, and then since x equals y cubed, x of t would equal y of t cubed, right? So in other words, x of t equals t cubed. Okay. So I put those together and I get what? T cubed t is my parameterization, which I'll write as r of t. Okay, so that's the parameterization of my curve. Next step, convert everything. All right, so I want to convert the integral. So my e to the x, what does that become? Well, I replace x with t cubed. Okay, and then I need y prime of t. What's it? Well, no, excuse me, I'm integrating with respect to x, right? So that becomes x prime of t dt. What's x prime of t? 3t squared, right? All right, and then what are my bounds for my integral? The bounds of my integral, so what t value gives me that starting point? T equals -1, right? And then what t value gives me that endpoint? Should just be 1. So that's my integral, and again, it's fairly easy u substitution. U equals what? T cubed. Du equals 3t squared. So it just becomes e to the u du. And that should be my solution. Integrating or finding the line integral with respect to y is the exact same. It's just I would do everything in terms of y instead of x. Now again, by itself, these line integrals with respect to x and with respect to y are not too interesting, but they're going to become useful in this section. Okay, so my last thing I want to do is line integrals for vector fields, and now this is where our material for 16.2 connects to 16.1. All right, so now instead of integrating a function, instead of just having a function fxy, from R2 to R, instead of integrating that along some curve C, I'm going to be considering these vector fields. So remember what these vector fields are. They're functions like R from R2 to R2. Okay, so what does that kind of integral look like? I'm still going to be integrating along a curve, but what does it look like when I integrate instead of a function R2 to R? What's happening when I integrate a function R2 to R2? Okay. Now, the way the textbook presents this information is they kind of give a physics example of doing work, and that's kind of how they introduce the idea. I'm going to do it a little bit differently. I'm going to kind of give a very general mathematical explanation, and then you'll probably, I assume, see a lot of physics examples in your homework. Okay, so let's consider a vector field from R2 to R2 or R3 to R3. Let's say R3 to R3. Okay, now what's going on? For each point x, y, z, we plug it into our function and we get an output. F1 xyz, F2 xyz, F3 xyz, right? It gives us the input of, we plug this into our function and we get a vector output, right? Okay, so that's what's going on. Now that's just talking about the function f, okay? Now we could think of f1 xyz as like the amount of our output pointing in the x direction, right? Like this is the output in the x direction, this is the output in the y direction, this is the output in the z direction. That's one way to think about it. Okay. And now let's consider a curve. Okay, so let's say this is my domain R3. Okay. I'm integrating, and now instead of integrating like over all of R3, I just want to integrate my function f along that curve. Okay. But before we forget about the integration thing for a second, just think about this curve. Let's say I want to try and add up all the outputs along that curve. So like a vector field, what does it do? I take each point in x, y, z, I plug it in, and it gives me a vector, right? It gives me these outputs. And I have an output for every single point. And, usually when I'm drawing these little arrows, I just pick, a relatively few amount. It might be like 500 or whatever, but I just pick a bunch of points and plug them in, and I kind of draw those arrows. But really, there's an arrow for every single point in R3. What if I wanted to take all the points in along my curve, right? Let's say, I consider all the outputs along my curve. Okay, now maybe the output for this vector is pointing in this direction, but I could break that down. I could kind of decompose it into pieces, right? Like in particular, all right, this vector is kind of pointing off this way, but it is pointing to some extent along my blue curve, right? So let's say I kind of want to take these values, these vectors, and I want to figure out how much of those outputs are pointing along my curve, and I want to add up all those outputs along the curve. That's essentially what this line integral of the vector field is going to give us. We want to try and add up the amount of output pointing in the same direction as the curve C. The question is, how do we calculate that? So let's assume this curve C has this parameterization, by this vector valued function R of t equals x of t, y of t, z of t. Okay. And let's think about our vector field along that curve. So let's say I plug the point x0, y0, z0 into my vector field, my function R2 to R, or R3 to R3, and I get that green vector. So at this point, my output of my function is pointing off in this direction. Okay, how much of that green arrow is pointing along the curve, right? Well, first, how much of this green vector is pointing in the same direction as my blue curve? First, we got to ask, okay, well, at this point, what is the direction of my blue curve? In which direction is my curve moving? Well, that's all about the tangent vector at that point, right? We're saying this blue curve is R of t. So at this point, my curve is pointing in the direction of the tangent, right? So at that point, at this point, my curve is pointing, and let's say t0 is the value of the parameter that gives me that point. My curve is pointing in the direction x prime of t, 0, y, t0, y prime of t0, z prime of t0. Okay. So that's the direction of my blue curve at this point. Okay, so that gives me like a tangent vector, right? But we want to consider the unit tangent vector because, tangent vectors can have all these different lengths, and what do the lengths mean? And that gets all confusing. All we care about is the direction. So we should be considering unit tangent vector. Okay, so let's consider t, capital T of t0, which is r prime of t0 divided by its own magnitude, right? All right. Now we have these kind of two ideas. We have my vector field output in the green, and then we have our unit tangent vector pointing in the direction of our curve. So how much of the green vector field is pointing in the direction of the curve, that same direction of the white arrow there? Well, to do that, to figure that out, we just take the dot product of those two. We want to take the dot product of the vector field with the unit tangent vector. But for this to make sense, we need this x, y, and z. We need everything in the same units, right? So this, since this is in terms of t, we want to convert this into terms of t as well. So that process is the exact same as what we've done before. We just replace our x, y, and z with our parameterization, whatever our parameterization of our curve is. Okay. So x becomes x of t, y becomes y of t, z becomes z of t. Okay, and now everything's in terms of t. Now I can take a dot product, right? And remember this unit tangent vector, well, that's the same as r prime of t over magnitude r prime of t. And then we want to integrate with respect to arc length, right? So remember, this is our term that gives us with respect to arc length. Okay, so we're back to integrating along the curve. Okay, so now we're not talking about integrating with respect to x or y. I'm integrating along the curve again. So I want to integrate with respect to arc length. So I have this arc length term here. But look at this arc length term really closely. This square dx dt squared dy dt squared plus dz dt squared. Well, what is that? That is the magnitude of our tangent vector. That's our magnitude, you know, our prime of t. Okay, so that square root term is just r prime of t, the magnitude of r prime of t. So that cancels with this. Okay, so we have a nice cancellation in this case of vector fields. These r prime of t is canceled, and my formula I'm left with is just this: f x of t, y of t, z of t time dot. This is dot r prime of t. There should be a dot here. I take the dot product of r prime of t, then I integrate with respect to t. Okay, and where am I integrating? Again, a is my t value, that gives me my starting point of my curve. B is my t value, that gives me my ending point of my curve. Now, before we go too much further, let's say there's some notation to talk about here, but before we go too much further, let me just pause and get an example for you guys to do. Okay, let's see, I got my handy dandy textbook out in front of me, so let's pick a problem and do a problem from these vector. Oh, did I stop screen broadcasting? Nope. Let's pick a problem from the vector field section. Do that real quick. Okay, right about here is where it should go. Okay. How about number 19 in the book? We're told to integrate, and now it's a two-dimensional vector field R2 to R2. And the vector field's written like this: xy squared minus x squared, xy squared I minus x squared j, using that ijk notation. Okay. And then we're told our r of t which is our curve, right? Our curve is r of t equals t cubed I plus t squared j. Okay. And I want to, and then we're told, okay, t is between 1 and 0. Okay, so I want to evaluate the line integral for this vector field along that curve. Okay. So I have my r, what's my formula? I need to take a dot product, right? Okay, well, I'm told my t is between 0 and 1, so that should be my bounds of my integral. What's my f of xt, f of y, f of xt, yt? Well, let's see. Let's kind of rewrite this as a vector. Maybe it'll be a bit clearer. This vector, I could rewrite this in vector notation as xy squared negative x squared, right? Okay. And now I want to convert this to in terms of t. I want to convert everything in terms of t. Well, for my curve, I know this is like saying, again, I could convert this to vector notation. This is the same thing as t cubed t squared. So my x is t cubed, my y is t squared. So I need to replace all my x's with t cubes, all my y's with t squared. So my vector field x becomes what? T cubed times t squared, so x times y. Well, t squared is y, and then I square it because it's y squared, right? All right, and then okay. And then let's see, negative x squared. So I take x, I replace x with t cubed, I square it, and then it's negative. Okay, so that's my fx, y. Then I take the dot product with r prime of t. Okay, so that's r of t. What's r prime of t? 3t squared, 2t. Okay, and then I have dt. Okay, so I need to find this dot product, and then I need to integrate. So let's first find the dot product. Okay, I could simplify this. I have t cubed times t to the fourth is t seventh, negative what? T to the sixth. Okay, dot product 3t squared 2t. Taking the dot product, that should become uh, 3t to the ninth minus 2t to the seventh dt. I integrate. From 1 to 0. I get 3 over 10 minus 2 over 8. And what is that? How about 24 over 80 minus 20 over 80, 4 over 80, 1 over 20, or, let's see, 0.05. Okay, now let's check. Is that the answer for number 19 in the textbook, section 16.2? Drum roll, please. 19, 1 over 20. Excellent. Now, some notation. These notations all mean the same thing. Taking the integral of the vector field along the curve, C. Okay. You might see it as expressed as f dot dr along C. You might see it as f of rt dot r prime of t dt. And this is the form most closely related to what we've just done. You might also see it as f dot capital T ds. All those mean the same thing, taking the line integral of the vector field along the curve C. Now, real quick, just to wrap up and connect to those annoying line integrals with respect to x and y real quick, we can write these line integrals of the vector field with respect to line integrals with respect to x, y, and z. So remember our vector field f from R3 to R3, we can think of that as a vector, the output as a vector like this, where the first component, the x component, is this function of x, y, and z. The y component is this function. Third component is this function. And okay, if we want to just make it a bit more distinct, instead of writing f1, f2, f3, let's write p, q, and r. Okay, so this is our vector field. Okay, well then let's write the line integral of the vector field. Excuse me, solicitor was calling. Said spam risk on my phone. So the line integral of the vector field along our curve C, we could write it like this. Maybe I should write, this stuff in here should be what? F of R of t. That's more in keeping with our notation, right? All right, well, what is this? Well, let's write it. How about let's write it like this? It's going to be more clear if we write it like this. Remember what this vector field is. We can write it like this, right? So let's just replace f, x, y, z with that. Okay. All right. And really, the x, y, and z maybe it would be most clear. Well, let's leave it like that for now. And then I take the dot product, r prime of t, right? And then just expand that dot product. And what do you get? You get p of xyz times x prime of t plus q of xyz times y prime of t, r of xyz times z prime of t. And then that's all multiplied by that differential dut, meaning we're integrating everything with respect to t. And then just kind of distribute that d of t to everything. And let's add a step in here. So really it becomes all right, this plus this now look at each of these. This is the line integral along our line with respect to x, right? That kind of annoying type of line integral we saw earlier. And then this one is the line integral with respect to y, and then the line integral with respect to z. Okay, so we've taken our line integral that's actually along our curve with respect to arc length, and then we've broken it down into these three separate integrals along the x, y, and z axes. Okay, so this only works in this case of vector fields. It doesn't matter if we're doing it in 2 dimensions or 3 dimensions, but it has to be for vector fields because we get that nice cancellation that allows us to break this up. Okay, so we can write it like this. And then remember, we have this shorthand notation where we can write it all as one integral and kind of drop, technically there's like integral signs in here, right? But we're just dropping those, and then we're using this shorthand notation. All right, let's see. Should we do? Are we going to get anything? don't think you're going to get anything from another example, so we'll save the examples for lecture. All right. It's 4:20, so you know what that means. It means our test review is in 10 minutes. So I'll see you there.